It was not supposed to be there. In January 2024, a team of astronomers using the James Webb Space Telescope pointed their instruments at a tiny patch of sky in the constellation Fornax. What they were looking for was light, ancient light. Light that had been traveling through space for so long that the universe itself had stretched and reddened it beyond what any previous telescope could detect. What they found broke the record. The galaxy, catalogued as jwst Z14-0, formed just 290 million years after the Big Bang. Its light has been traveling toward us for 13.5 billion years. At a confirmed redshift of 14.18, it is the most distant galaxy ever spectroscopically confirmed in human history. And it is 1,600 light-years wide, packed with hundreds of millions of stars, already glowing with oxygen, a heavy element that requires multiple generations of stellar birth, life, and death to produce. In 290 million years. Our current models of how galaxies form, models built over decades of observation, refined by thousands of scientists, validated across billions of light-years of data, say this should not be possible. Before this video is over, you will understand why that galaxy is only one of several things the James Webb Space Telescope has found that scientists cannot yet explain. But to understand why these findings are so unsettling, you first need to understand what scientists expected to find, and why they were so certain they were right. The James Webb Space Telescope, launched on December 25, 2021, carried into orbit by an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana. Its primary mirror spans 6.5 meters, more than 2.5 times the diameter of Hubble's mirror. Positioned approximately 1.5 million kilometers from Earth at a gravitationally stable point called L2, its tennis court-sized sunshield permanently blocks light from the Sun, Earth, and Moon, allowing its infrared detectors to cool to negative 233 degrees Celsius. It cost approximately $10 billion and took 25 years to build. The scientific community had specific, quantified expectations for what it would see. Those expectations were not guesses. They were the product of the most successful cosmological model ever constructed, Lambda CDM, which stands for Lambda Cold Dark Matter. This model, refined over 4 decades and validated by the Hubble Space Telescope, the Planck satellite, and ground-based observatories worldwide, makes precise predictions about how the early universe assembled itself into galaxies, stars, and structure. The model predicted that in the first few 100 million years after the Big Bang, the universe was relatively simple. Hydrogen and helium gas gradually clumped under gravity into small, dim, irregular structures. These were the first galaxies, small, faint, sparse. The universe was thought to be too young and too diffuse to have produced anything large or bright. Webb was expected to confirm this picture. Instead, it found something that Stefano Carniani, of the Scuola Normale Superiore, the lead author of the jwst Z14-0 discovery paper, published in Nature in September 2024, described with a single word: stunning. The galaxies that should not exist, jwst Z14-0, is not an anomaly. It is the most extreme example of a pattern that Webb has been revealing consistently since its first deep-field images were released in July 2022. In those first images, released to the public within months of the telescope reaching operational status, researchers immediately noticed that the early universe was brighter than it should have been. Galaxies at redshifts above 10, corresponding to the universe's first 500 million years, were appearing in Webb's data in numbers and sizes that exceeded predictions. Not by a small margin, by factors of 10 to 100 in some cases. A study published in the Astrophysical Journal in June 2024 by researchers at the University of Missouri examined 300 unusually luminous objects detected in Webb's deep-field observations. The study, published on June 27, 2024, described these objects as candidates for some of the earliest galaxies ever observed, and noted that their brightness and apparent structure challenged current understanding of how rapidly the first cosmic structures could have assembled. The problem is not merely that these galaxies exist. The problem is what they contain. jwst Z14-0 shows clear spectroscopic signatures of oxygen. This matters because oxygen is not a primordial element. It does not exist naturally after the Big Bang. Oxygen is forged inside the cores of massive stars through nuclear fusion, and it is only released into the wider galaxy when those stars explode as supernovae at the ends of their lives. Then a new generation of stars must form from that enriched gas, and another generation, and another. The presence of oxygen in a galaxy that formed just 290 million years after the Big Bang means that multiple complete stellar life cycles, Birth, fusion, death, dispersal, reaccumulation, and reignition had already occurred, in less time than it takes light to cross a modest galaxy cluster. Researchers do not yet have a consensus explanation. Some scientists propose that the first stars, called population 3 stars, may have been far more massive than models predicted, burning through their fuel in millions of years rather than billions. Others suggest that early density fluctuations were larger than standard models assume. Both hypotheses are under active investigation. Neither has been confirmed. What has been confirmed is that our picture of cosmic dawn, the period when the first light appeared in the universe, is incomplete. The expansion problem. The early galaxies are not the only thing Webb found that scientists cannot explain. In early 2024, a team led by Adam Rees, an astrophysicist at Johns Hopkins University and co-recipient of the 2011 Nobel Prize in Physics for the discovery of the universe's accelerating expansion, used James Webb data in combination with Hubble Space Telescope data to make a definitive measurement. The result, confirmed with additional data through 2024, resolved a question that had been open for years. It resolved it in the most troubling possible way. The question was this: how fast is the universe expanding right now? The answer, expressed as a number called the Hubble constant, can be measured two different ways. The first method uses the cosmic microwave background, the oldest light in the universe, emitted approximately 380,000 years after the Big Bang and mapped by the European Space Agency's Planck satellite. This method gives a value of approximately 67 to 68 kilometers per second per megaparsec. The second method uses nearby distance markers, Cepheid variable stars and Type 1a supernovae, to measure how fast galaxies are currently moving away from us. This method consistently gives a value of approximately 73 kilometers per second per megaparsec. Those two numbers do not agree, and they cannot both be right. For years, the most optimistic explanation was measurement error. Webb was expected to settle this by providing the most precise measurements ever made of the Cepheid distance ladder, checking whether Hubble's measurements were contaminated by crowded stellar fields or calibration errors. Rees's team used Webb to observe more than 1,000 Cepheid stars across 5 galaxies, out to approximately 130 million light-years. Webb's superior resolution allowed them to separate individual stars in regions where Hubble saw only blurs. The measurements confirmed Hubble's results with greater precision than had ever been achieved. The discrepancy is real. It is not a measurement error. It is not a calibration problem. Two of the most sophisticated space telescopes ever built, using independent methods, now confirm that the universe is expanding at different rates depending on how you measure it. And the difference, approximately 8% between the two values, is large enough that it cannot be explained by any currently known physics. This problem has a name. Scientists call it the Hubble tension. Adam Rees stated in March 2023, with two NASA flagship telescopes now confirming each other's findings, we must take this problem very seriously. It's a challenge, but also an incredible opportunity to learn more about our universe. The phrase to focus on is learn more, because right now, as of 2025, the Hubble tension has no accepted solution. Proposed explanations include early dark energy, a hypothetical form of energy that may have briefly influenced the universe's expansion rate shortly after the Big Bang. They include modifications to general relativity. They include new forms of dark matter. None of these proposals have been confirmed. All of them, if true, would require revisions to cosmology at the most fundamental level. The universe was Messier. Earlier, there is one more category of Webb discovery that researchers are still working to understand, and it concerns not just what the early universe contained, but how it was behaving. In January 2025, a team at Texas A&M University announced the discovery of a system they named jwst Quintet, 5 galaxies in an active merger event at a redshift of 6.71, corresponding to approximately 800 million years after the Big Bang. The discovery, published in Nature Astronomy, showed that the colliding galaxies were already surrounded by a halo of oxygen-rich gas, extending beyond the boundaries of the galaxies themselves. The lead author, Dr. Wida Hu, stated that the system showed processes, complex multi-galaxy mergers, widespread chemical enrichment of intergalactic space, that were not expected to be common until well over 1 billion years after the Big Bang. The standard model predicted that early galaxy interactions would be simpler, 2 galaxies merging perhaps. Gradual chemical buildup, slow structural assembly. Webb keeps finding the opposite. Complex systems, rapid chemistry, structures that look mature where the universe should have been adolescent. Here is the fact that recontextualizes everything described so far. In the lambda CDM model, the universe's structure grows hierarchically. Small things form first. Then they merge into larger things. This is called bottom-up structure formation, the dominant cosmological framework for decades. Every early galaxy Webb has found that is too large, too bright, or too chemically enriched challenges this framework in a specific, quantified way. Scientists are not saying the standard model is wrong. They are saying it is incomplete. There is a difference, but the incompleteness being revealed by Webb is not in the margins. It is in the foundational period of cosmic history, the first billion years, that the model was specifically designed to describe. What comes next? Webb is still operating. As of 2025, it remains in its operational orbit at L2, and NASA estimates it carries enough fuel to continue science operations well into the 2040s based on the precision of its launch trajectory. The questions it has opened are now driving the next generation of scientific investigations. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will survey far wider fields than Webb, providing statistical samples large enough to test whether these objects are unusual or representative. Ground-based observatories, including the extremely large telescope, currently under construction in Chile, will obtain detailed spectra of the galaxies Webb has identified, revealing their chemical compositions in far greater detail. The Hubble tension is being attacked from multiple angles simultaneously. New cosmic microwave background measurements, new supernova datasets, and gravitational wave distance measurements, an entirely independent method, are all being pursued with the urgency a genuine foundational discrepancy demands. And the early galaxy problem is generating new theoretical models at a pace that reflects genuine scientific excitement. Not panic, excitement, because the history of physics is full of moments when a confirmed anomaly pointed the way toward a deeper and more accurate understanding of reality. The photoelectric effect pointed toward quantum mechanics. The orbit of Mercury pointed toward general relativity. The accelerating expansion of the universe, discovered in 1998, pointed toward dark energy, a concept that revised our understanding of the universe itself. The anomalies James Webb is finding may point toward something equally significant, or they may be resolved by smaller adjustments to existing models. That is genuinely unknown. What is not unknown is that Webb is functioning beyond its design specifications, seeing further than any instrument in human history, and returning data that is forcing the builders of our best cosmological models to revise them. That is exactly what science is supposed to do, and always has. The universe turned out to be stranger than the models predicted. It always does, every single time. Which of Webb's discoveries do you find most difficult to wrap your mind around? The galaxies that formed impossibly fast, or the universe expanding at two different speeds simultaneously? Drop it in the comments. If this gave you something to think about, subscribe. New video every week. See you in the next one.